Okay, so last but certainly not least is the bandpass filter that is derived from cascading RLC filters, low pass and high pass filters. So the criteria were to have two cascaded sections of the LPF and two cascaded sections of the high pass filter. So we can see here that here is our LC Pi filter. That's actually just the middle part here. Um, but there's a bit of an issue with just having that. We have to include extra resistances, especially on the front. Without this resistance on the front, the voltage, the Vn essentially, it is identical across this capacitor. So the capacitor ends up being excluded from the transfer function, and we don't actually end up with the transfer function for the LC Pi filter. So whenever we include this resistor here, that divides the voltage so that we actually end up getting this involved in the transfer function. And it creates a LPF here, an RCLPF, which then becomes one of the sections that we cascade with the RLC part of the filter over here. The resistor on the end here is to help with the derivation of the transfer function, or is to help with the impulse invariance derivation of the transfer function, or the z domain transfer function. That is, it allows us to sort of complete the square in the denominator, and we'll see that happen there. And you'll also see it happen with this one here as well. And then same story for these resistors on the high pass filter. We end up getting an RL filter here, and I'm not sure if that's a high pass filter or not. I don't think I've ever made an RL filter in my time in any sort of electronics class or anything like that. But we do know that for LC filters specifically, they work by creating resonance, or essentially by attenuating all signals except for a resonant frequency, which is given by 1 over the square root of LC. And so because of that, whenever the L and C are identical, whenever they're at a certain point, the voltage, I'm trying to think of this correctly, but the reactance, yes, there it is. At some point, at some frequency, the reactances of those components match up and they cancel out, and all the current is allowed to flow, and so you see a resonant peak in your filter. So, with that said, now we will go ahead and walk through the derivation. So we can easily get the RC and RL filters here, just like this, but getting the RLC high pass and low pass filters is a bit more complicated. So I just did some basic circuit analysis that we learned in Circuits 1. Go back to the basics, ha ha ha. And we end up getting this differential equation, which we can then use the Laplace transform to bring it into this form, and then we get the transfer function like this. We end up switching around some of the values here, and like I said before, in order to complete the square, we have this 1 over RC value and 1 over LC, and we sort of relate them via these two substitutions. So when we look in the denominator, that's a perfect square. And this allows us to be very cheaty whenever we do the impulse invariance derivation of the transfer function. And that's for the low pass filter, this transfer function right here. So then we move on to the RLC high pass filter. Again, I just analyzed the circuit and got a equation with a bunch of integrals, which the integral is just S inverse. So we get S inverse, S to the second, S to the negative 2, and then S to the negative 1 here. And then we just algebra our way to the transfer function, and again perform that nice substitution thanks to the resistor. Yes. So Here in the end, here are our two transfer functions. In the end, we have the two cascaded sections. This is our LPF, RC LPF, and our LC LPF. And then here is our RL HPF and our LC HPF, or high pass filter. I just use the acronyms because that's me right now. So first we're going to start with the impulse invariance technique. It's pretty much the same story as the RC filter derivation. This part right here, at least, because that's really what it is. So bam, 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 bam. Sorry, bam, 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 bam. There. There is the transfer function for the RC low pass filter. The LC low pass filter is given here. So I sort of did them at the same time, which is a little bit confusing to look at. But as you can see, once we get it into this form, that matches with a nice pair, an inverse Laplace transform pair. So we get this exponential with a t in front, and we form the substitution t equals nts. Then we do a substitution with these alphas here. I mean, alpha 1 and alpha 2. And this is just to make the discrete time domain versions look like something that has a nice Z transform pair. So we then just transform those again, and we get our final transfer function here. So just like in the RC LPF, the first order RC LPF is very simple. And then here we have the LC LPF, which is second order. And here we go again for the high pass filter impulse invariance technique, just inverse Laplace transform. But this time we have s's in the numerator, and so we get some derivatives. We get a little double derivative business here, which is a pain. But you can see here we went ahead and just solved it there. I'll walk through it a bit slower, actually. So this first section is, we're just going to take one derivative through, and since we have t, e to the t, and u of t, all those together are going to form, we're going to do some sort of product rule again. And so we end up, this first part was where the t was taken, and then here the e to the minus t was taken, so we get a minus right there. And then I just pulled the u of t out from both of those two. And then we have the third part here where the u of t was we took the derivative of u of t and got the Dirac delta. And then we have to take the next derivative of all of this. So for this section right here, it's just like all of this again. So we end up with, I think this right here is what I'm talking about, this piece right there. And then we have the other parts where the u of t wasn't taken in the derivative. So this is just really complicated. The part that I want to draw attention to, we're gonna draw attention to important parts now, is the stuff with the Dirac delta. So I did some research on how to take the derivative of the Dirac delta, and I found a lot of stuff saying that Dirac delta isn't a function of specific points, but it's like a distribution of functions or something like that. I'm not sure if that makes any sense, but it brought me to this down here. When you take the derivative of the Dirac delta, there's some associated function with the Dirac delta that you then take the negative derivative of. So, and that would be this part right here. So we actually take the negative derivative of this multiplied by the Dirac delta, and that is how you do the derivative of the Dirac delta in continuous time. Something like that. We'll see in the end that it didn't even matter. Because at the end of the day, we end up evaluating all of this at 0. And so this part goes here. So we evaluate this exponential at 0 and this exponential at 0. this t goes to 0, so that goes to 0, but this goes to 1, and so we get 2 times 1 times the Dirac delta. And then this part right here, also, sorry, this part was right there. This part was right there. So this over here is this. And again, it's evaluated at 0, so we get a Dirac delta here and then a Dirac delta here. And so this becomes 2 times the Dirac delta, and this is minus 1 Dirac delta, gets us just a whole Dirac delta right here, which we then finally decide to evaluate it at 0, which gets us just the Dirac delta there. And then this whole first part comes from up here. I think it just cancels out with the rest of the stuff somehow, somewhere. Anyway, so then we perform the substitution t equals nts, and then we perform the substitution alpha equals e to the minus omega LC TS to get it into a form that has the nice pairs, and then we just perform the substitution for the z transform pairs, and we get this, which we then get by algebra stuff. We end up with this. I think we had to multiply top and bottom of this 1 over ts by 1 minus alpha z inverse, which you can see here. And instead of doing ts, I just did fs. And so there we go. And then I believe this h2 of z, so we have 2 here. We have h1 of n must be from the low-pass filter. Was not very organized. Yes, it's up there. It's from the low-pass filter. And then this is from the LC part. So there's that. And then here's this. I think I just had to multiply this by 1 minus alpha z inverse and this by 1 minus alpha z inverse quantity squared, and then just algebra it all together to get this. And then together they look like this. And so as you'll see in MATLAB, we'll just take the coefficients from this filter and just use the convolution to perform the necessary polynomial multiplication in order to get the full high-pass filter. And then, in order to do the bilinear transform, which is a lot simpler, we just do the substitution s equals 2 times fs times the quantity of 1 minus z inverse over 1 plus z inverse. Here's our substitution. For the LPFs here, we just multiply top and bottom by the 1 plus z inverse to the 2nd power. And once we do that, it becomes this up here. And then we just algebra our way over to this. So again, we have 2 parts, the RC LPF and the LC LPF. And as you'll see, I try to get a coefficient of 1 in the denominator for the first element, and I do that by dividing out the first denominator coefficient by everything. Okay, and then last but not least, the bilinear transform for the high-pass filter. We, of course, have to perform that substitution again, but now we have substitutions occurring in the denominator, but just like before, it's super easy to solve this just by multiplying the top and bottom by some power of the quantity of 1 plus z inverse. In this case, it was 2. And I went ahead and took this here and simplified it, and then took this over here and simplified it, and then just included the other one right there. So there is our theoretical derivation. Now we're going to move into MATLAB and see this work in nicely. And unlike the RC stuff, both the impulse and variance technique and the bilinear transform technique work. And we'll see that. So first off, we'll do the impulse and variance technique because that's the one that always comes first. You can see I'm also running the simulations here just to be sure that everything is probably going to work on the DSP board, but again, like I showed with the RC filter stuff, sometimes it just doesn't. Okay, so I think we're good. run it here. There's our resulting bandpass filter. Here's our simulation. Let's look at some of that stuff. So for this filter, our low cut for the high pass part was 100, and our high cut for the low pass filter was 8,000. Again, it's backwards because we want a band pass filter, so we want the low pass filter to have a high cutoff frequency and the high pass filter to have a low cutoff frequency. And then our test frequency for the simulation was 20 hertz sine wave or cosine wave, and you can see it here. It attenuates almost immediately, which looks nice. If we go ahead and look at the frequency response of our filter, both the impulse invariance and bilinear transform techniques show up pretty well. The impulse invariance part of the high pass filter, again, didn't give me too many issues. If we look at that right here, it's a pretty nice scaling. It's very aggressive on the lower frequencies. But let's go ahead and look at this. So, smack dab in the middle of our pass band seems to be around 900 hertz. And then, like we said, the bandwidth is from 100 to 8,000. So let's look at that. There is 100. Yes, 100 and 8,000. It's going to be right about there. Yep, and it's negative 9 dB because we have the initial RC filter, which is negative 3 dB, and then the LC filter, which might also be negative 3 dB, but it might be negative 6, because I think that LC filter was second order, if we recall. If we go back to the theory, pretty sure it was second order. Yeah, it's a second order filter. So it's twice as angry or aggressive at the attenuation. So I'm going to go ahead and load this onto the DSP board. Then we'll run some music through it. Okay. Filter is running, and I'm not getting any nans, so that means we're good. I'm gonna pick a okay. Let me pick a noisier song here. Actually, the music isn't a good way to do it now. Analyze the filter. Noise would be better. But while this is playing, let's go ahead and look at our cutoff regions. You can see we don't have much going on below 100. And then beyond 8,000, which is about right here. There's about 8,000. We're not seeing much up here. Now, in order to make sure that that's just not how the song is, I'm going to go ahead and up the high frequency to 16 and the low frequency to, I don't know, like 10. We're just going to open it up. It'll be beautiful. Yes. New coefficients means new debug session. right? Of course. Rewind the song just a bit here. There we go. There's some nice frequencies coming through on the high and low ends here. But just to be sure, let's go ahead and do noise instead. No, this is a gorgeous song. Really helps to release the tension after trying to simulate RC filters in real time. There we go. So, with this, we had our cutoff frequencies pretty much wide open, so we don't see a lot of attenuation here. And again, this is Gaussian noise, so on the spectrum on the right, it shows that Gaussian thing sort of decrease, but on the left here, we can see that this is what we should be expecting. So let's go ahead and change the filter around a bit. We'll bring the cutoff frequency to like 5,000 and between 1,500 and 5,000. That sounds fun. There we go. And again, this is the impulse invariance, so follow the blue line here. So we should see major cutoff at around between 1,000 and 100 is where we see it really drop off, and then over here between 10,000 and above is where we see it drop off. Really, actually, about 800 and above there. Sorry, 8,000 and above. There's our new filters. Load up the coefficients. My brain is so cloudy right now. Okay. Next, we're going to play. And let's look at this here. Perfect. That's what I like to see. So, as you can see, we get nice. In the pass band, we expect it to be between 1,500, which is about right there, and 5,000, which is right there. So between here and here, yeah, obviously. So that was just the impulse invariance form of the filter. So let's do the bilinear transform. And we're gonna. I forgot to show my code actually doing it. So before I bring the bilinear transform onto the DSP board, I'm going to walk through the code real quick. So it's just like everything else I've done. I call a function to generate the coefficients, and then I do some plotting first just to check to make sure the low pass and high pass filters look good, which is what you see here, 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 and here. Then I go ahead and convolve the low pass with the high pass, and I use the So then we have here's the impulse invariance. Those the B coefficients and then the A coefficients for the impulse invariance, low pass, high pass, and then the bilinear transform right here, low pass, high pass, numerator coefficients, low pass, high pass, denominator coefficients. And then we'll simulate the filter using the bilinear transform version. And we'll write the bilinear transform coefficients to the coefficient file. So after we do this convolution, we again just get this response using the freq command that just generates the impulse response of the filter in the frequency domain, and we can see it here. There's the impulse invariance, and there's the more dramatic bilinear transform. And you can see, I haven't pointed this out in the other ones, but you can see this warping that really happens with the bilinear transform versus the impulse invariance. So you essentially have to really increase the you have to increase the cutoff frequency more and more and more each time in order to get you get diminishing returns on the bilinear transform. I'm thinking of the graph in my head that was given in one of the lectures or books or something, but it's not helping. So anyway, you can see it here most of all. Whereas for the impulse invariance, it just goes down and then stops at about between negative 45 and negative 50 dB. But the bilinear transform just drops off so hard because it takes a lot more. I'm trying to think of the way to say it, but I guess I don't really understand it much myself. I mean, it warps. That's pretty much the only way I can explain it. Okay. Well, with that said, we're going to go ahead and generate these coefficients. These are the bilinear transform pair coefficients. And if you look at MATLAB, you should expect something that already looks like this, because this was the impulse invariance one. So let me flash the DSP board with the new filter, and fingers crossed we don't get any nans this time. Awesome. So there we go. Let's go ahead and open it up some more. I want more low frequencies. I'm going to drop this down to 500. It isn't a massive change, but we should definitely be able to hear it, which is the important part here. There you go. Yes. Very good. Okie doke. That pretty much covers all the stuff for the LC filters. And that was the last section of the project. So, I want to mention one last thing about the whole rounding issue. So, this is something that future generations of RTDSP students might want to keep in mind. We set the format to long here in MATLAB. We set the format to long in MATLAB to get long doubles, which are essentially 64-bit doubles, which is what we definitely want on the DSP board as well, because that's where the actual real-time filtering is happening. But by default, the code provided in the book is only single point floating number, or single precision floating point numbers. So in order for us to get the actual 64-bit double precision floating point numbers, we have to change anything that says float to double or long double. Double or long double aren't always the same depending on the compiler that you're using. In Code Composer, with the compiler that I'm using, I noticed that double and long double were the same, but long double is always going to be the 64-bit version. So that's essentially what I did. I made a change to the file that writes the coefficients. Here it said extern float. I now have it saying, pretty much anywhere where it said float, I have it say long double now. Long double, long double. And this is just so that when we load it into Code Composer, it treats all the data as double precision floating point numbers, which helped me be able to get these filters to work at higher sampling frequencies, where before it had to be at like 8,000 sampling frequency for this to even work. And you could even see I was unsuccessful to get even the RC filters to work just because of those rounding errors. But the higher precision definitely helps. That's the last thing I'm going to say. All right, that is it. Thank you for watching.